the idea of a tritium panel was first raised. It was raised in the context of a way to express our appreciation to John Bockris and his contributions. John was still alive at the time, and it's for me, it's sort of poignant because we had intended to say very good things about John when he was alive, and I'll spend a few moments saying mostly good things about John now that he's passed on. But in addition to the personal and social context, the question of tritium and why are we talking about tritium now and why are we revisiting old work, it is, in my view, still the clearest evidence of a nuclear effect in the deuterium-palladium system, the Fleischmann-Pons domain. The clearest evidence of a nuclear effect is the tritium evidence. It's clear, it's unarguable, it is produced in an electrochemical experiment. Just the fact that a nuclear process occurs in an electrochemical experiment, independent of any considerations of heat, is already stunning. And any theory, any reasonable theory, must account, I think, first for tritium and second for heat. The evidence in my own work of tritium, we worked for years and years monitoring every cell for tritium production. We probably worked through 500 tritium assays before we saw any tritium at all. And the tritium evidence that convinced me most in our own work was the work that we did in replicating the experiment of Arata and Jean, in which we saw very, very substantial increase in helium-3, and later determined that helium-3 was the decay product of tritium that had been produced in the experiment. So I'm convinced from my own work, and there's a sort of attitude in this field, maybe an attitude in every field, but it's certainly present in this field, that it isn't true if you didn't do it in your own laboratory. And there are plenty of people in the world still, I think, who believe the tritium and don't believe the heat, or believe the heat and don't believe the helium. If you've done it yourself and seen it yourself, you become much more easily convinced. It's actually far more efficient if you can convince yourself from the work of others. You have to do a little less work. The work of tritium sort of burst upon the scene in what I call a triple discovery. Simultaneously to me, I learned of the work of John Bockris and Nigel Packham at Texas A&M, producing very significant amounts of tritium. The work at Bach that was reported to us by Srinivasan and Iyengar, who came through on a whirlwind visit in 1989, late 90, early 90, and a massive amount of work had been done at Bach, a lot of observations of tritium, and then the work that Ed Storms did with Carol Talcott. I could tell you stories about that too, but I won't. But that these three things came simultaneously, like a bolt from the blue. So not only replicated, but the replication was replicated before I even heard about it. So that's why these people are here. That's why Ed Storms and I thought that we would get together and talk about the tritium work, both to reinforce the need for a theoretical description of it, and to express our appreciation for the contributions of John Bockris in his aging then. I don't think anybody else in the room has had that sort of mixed pleasure and privilege of interacting with John Bockris at the height of his powers. John Bockris in England in Imperial College, I noticed the Matt's panel was all MIT guys. Well, in the world of electrochemistry, the MIT is Imperial College in London. And the one individual who determined that, made it happen, was John Bockris. John Bockris invented modern physical electrochemistry. John Bockris in England and Frumkin in Russia really created the field that we call electrochemistry. And without those guys, without John, I don't know where electrochemistry would be. I'm not even sure that we would have the present suite of batteries that we have. John's contributions were momentous. He certainly had more effect on my career than any other human being. I wrote a few words about John in Infinite Energy. He sort of swept into my life, came to be the external examiner on my master's thesis. I won't tell you how many decades ago that was, but he blew into the department at Victoria University of Wellington, New Zealand, like a gale force of wind, and basically seized control of the entire department for the period of time that he was there. He gave a lecture. He was asked to give a lecture. He got up in front of the classroom, a room as big as this, filled with mixed chemistry department, biochemists, geochemists, physical chemists, organic chemists, and he said, "I don't have a lecture prepared for you. Ask me a question on any subject." Don't do that to me, please. And for more than an hour, he fielded questions from this group of people. Via a wide, diverse range of chemical topics, and every one of these questions asked, John had read relevant papers on the subject and was able to write on the blackboard, chalk and blackboard, if you can remember that, the exact citation of the reference that he was speaking of, page numbers, names, date, and year, and direct you very often to something he had written in a citation to that, and make cogent and lucid comments about it. I was about to go off to England, and I thought, my God, you know, if they're all that clever, I will never survive. Good news or the bad news, I suppose, of the world is they weren't. It was just John. He was an absolutely towering force in electrochemistry, and in the early days, he was a towering force in the cold fusion field. And I might not have got into the field if it hadn't been for the fact that it was Martin Fleischmann and John Bockris, that my two heroes, who sort of led the charge. And I was willing to, just on the basis that those two giants were involved, I was willing to abandon everything that I was doing, fling myself into this field, and swim down the river with you all. So I think I would like to end with my deepest regret of John's passing. It was time, but he has influenced me more than any other scientist. With that sort of solemn note, I'll give the microphone to Ed to talk about the subject of today, which is tritium, and it's. With that, or do you want to do mic?
Well, I need to be able to change slides. So I need the other tool. All right. Well, first of all, I'd like to give you a tutorial about tritium itself before we talk about how you make it. Tritium is an isotope of hydrogen containing a proton and 2 neutrons. You all knew that already, but I had to be complete. It's a beta emitter with an average energy of a beta of 5.7 keV, maximum of 18.6. Has a 12.3 hour year half-life. The the energy is so weak that the beta can barely pass through a piece of paper. So detecting tritium is a challenge. You can't detect it with an ordinary Geiger counter. You have to use a number of other special techniques. It's found naturally in gas and deep vents in the earth, so it is manufactured in the earth. Because it has a short half-life, this has to be a contemporary reaction. It's also in the atmosphere from atom bomb tests, that's largely decayed away now, and by accidental release, which occasionally occurs from national laboratories, from exit signs that contain tritium breaking or being subjected to fire. It's present in all D2O. So if you get a bottle of D2O, it will have a small amount of tritium in it. And that has to be taken into account. It's a biological hazard in large amount, but in small amount, it's used in medicine as a tracer. At Los Alamos, when large amounts of tritium were used, and occasionally somebody would get a nose full of it, they would send you home with a case of beer and tell you to drink it all and then come back later. If you could. When it results from BB fusion by hot fusion, it is always accompanied by a neutron. And generally speaking, it's one neutron for one tritium and vice versa. So you can tell when hot fusion is occurring simply by the neutrons being present. The neutrons are not present during cold fusion. Because it has a low energy, it's detected by passing it through a detector containing an electrode that's at high voltage. The beta particle ionizes the gas that produces a small discharge. That discharge is recorded as a voltage pulse. That's one way of detecting it. The other way, the tritium is converted to water. The water is dissolved in an organic fluid that causes scintillation when the beta particle passes through it. That light is then measured with a photomultiplier detector. So and that technique is well documented, well known, unambiguous, and is quantitative. Well, now there's reason to question a claim, and there always is, and sometimes they're justified and sometimes they're not. And it's all in the mind of the beholder, of course. So the first that was suggested was contamination. We know that there's a small amount of tritium in the environment, therefore it could get in. And then of course they'd say, well, you work at Los Alamos and there's all kinds of tritium around at Los Alamos, and of course it gets loose, and of course it got into your laboratory, and then of course it got into your cell. And then we of course had to take that into account and go to a lot of trouble to prove that wasn't true. It's preferentially concentrated in D2O as a result of electrolysis. The deuterium leaves more quickly than the tritium does as a result of the net chemical reaction, and so the tritium content of the D2O, there was some there to start with, so the concentration increases. That rate of increase is well known. It can be removed by simple calculation. It does not exist if you have a closed cell because nothing leaves. Everything's captured. And so many of those studies were done in closed cell for that reason. For measurement, one of the problems with this scintillation technique is that when you put material into the organic fluid, a chemical reaction occurs which also produces light, called chemiluminescence. That light will confuse the signal initially. Usually it only lasts for about an hour, so you just sit around waiting patiently until it goes away and then make the measurements. The other technique is to distill the D2O containing the tritium and get rid of the chemicals that would cause this effect. And when that's put into the scintillation fluid, chemiluminescence does not occur. And then added on purpose, and we'll talk about that a little later. in the context of John Bockra's experience. But there was always a suspicion in the minds of some people that we were so desperate to prove that cold fusion was real that we would find some tritium somewhere and dump it into our cells and say, aha, see, we made tritium. That was a little insulting, and it got particularly nasty with respect to John's work, and we'll talk about that shortly. Well, the importance of tritium, it can only be produced by a nuclear reaction. And as Mike said, it's unambiguous. There's no wiggle room. This results from a nuclear reaction. And so therefore you have to take into account, you somehow have to explain and acknowledge that a nuclear reaction is occurring under normal conditions in these various pieces of apparatus, not just electrolytic cells. It's been made a number of different ways, all common to the cold fusion process. Because it's produced without neutron emission, it does not result from hot fusion. There is some other technique, some other method, some other kind of reaction that's required to make it. And yesterday, in my talk about theory, I explained how I think it's made. And of course, each of you are free to have your own ideas about that, which of course you do. Its presence is unambiguous, and it forces a direction to the explanation. Because once you admit that tritium can be made, automatically you are forced into a particular logic path towards an explanation of cold fusion in general and helium production in particular. Well, the evidence of tritium production has been worldwide. I'll show you a little bit of the early work done at the various laboratories around 1990. Chino will describe what was done in India, and they did an extraordinary amount of work. I mean, it's really overwhelming. And Tom Clater will describe his work using gas discharge, which is ongoing. All right, so let's talk about the measurements. The first measurement that was reported was by John Bockris, and this is his work. And this is the date. And it's on this basis that he's claiming with great pride that he was the first. And of course, there's a number of us who would like to be first, and we'll argue about that issue. But there were basically three groups that were working simultaneously and sort of hit the jackpot, if you wish, pretty much at the same time. And John's work, there's a graph that starts out here. And he was able to start this almost immediately because he knew Martin Fleischmann. And John was an expert electrochemist. He knew how to do these experiments. So he and the students jumped in immediately, proceeded to electrolyze, and it took a while for it to turn on, and then made measurements periodically. And of course there was zero here, and then there was almost zero here, and then all of a sudden you get this, and then you get this decay. The tritium does go away. There is a reaction that is using up the tritium. And I argue that the tritium can fuse just like anybody else can fuse. And so it reacts with the deuterium that's present to form other nuclear products. And that causes it to go away. Anyway, this was the first indication. And then, of course, that brought out the skeptics. And one of the major skeptics was Gary Taubes, who was in the process of writing a book at the time. And he went to the laboratory. He visited myself, but he also visited Bockris and interviewed the various people and came to the conclusion that this was perfect evidence that the graduate student had just simply added tritium at that particular moment. And so this was essentially fraudulent measurement. Well, that's the reason, you know, one can come to that conclusion, but he went one step further. He wrote a letter to Science magazine with this accusation in it. And Science magazine published that without any evidence whatsoever. Well, that, of course, made John Bacchus very angry, and so he also wrote, and letters were published about the exchange. There was also an investigation at Texas A&M to find out whether or not fraud was in fact committed. I even got into the act. I said, okay, let's see what will happen if you do add tritium. Oh, I happen to have tritium available, which of course made me suspect. So I added tritium, and you know, you get sort of this effect, but it doesn't decay away. It just simply stays constant, because the conditions that made the tritium allow it to decay away. And if you don't have the conditions to make the tritium, if you put it in artificially, you don't have the conditions for it to go away. Well, I sent that information to Science magazine and said, you know, we don't care. That's too much detail for us. Okay, so John took into account the effect of increased activity, that is, the separation factor. He took into account some chemiluminescence, and he made a lot of tritium eventually, 10 to the 12th atoms per milliliter maximum. Now, later on, as he perfected his technique, he got this data. Here is the tritium activity as a function of time, and two cells running simultaneously, same bench top, same power supply, same heavy water, same material. One showed nothing during this time, but the other cell was running 0, and then he increased the current. Now, looky here, it just went up, and he increased the current again, and it went up even faster. And the interesting thing, if he shook the cell, it stopped working. And it would take another several days for it to start working again. So something about the cell that could be changed by shaking was causing the tritium production. And it was, the identification of that is possibly a little ambiguous, but he examined the cell surface and it contained dendrites, fine wire, little projections of copper that were resulting from the wires in his cell. Well, was that the source? Who knows? But he developed a theory on that basis. He also had one other, what would I call it, chance sloppy event. His cells picked up light water, and that light water would accumulate in his cell, and he measured it, which was very good. Everybody else was working very hard to keep light water out of their cells, including myself. It would appear now that the tritium is made by the fusion of a proton and a deuteron, so light water is required. There's always a little bit of light water in heavy water, but if you add extra light water, you're going to get more tritium. And he was very lucky by being sloppy in that regard. And that's very true of a lot of the cold fusion. We had no idea how it was happening, why it was happening, what to do next. And nature would intervene, and our sloppiness would intervene, and give us just exactly the right conditions, and then it would work. But then you wouldn't know how sloppy you were, and the next time you did it, you weren't as sloppy, and so it didn't work. So that's why we really do need a theory. We need guidance. We have to know what we have to actually do. Because right now we're just trying this and trying that. Okay, I'll show you some of the work at Los Alamos. We set about trying to find tritium because trying to find heat was too difficult. Early on, tritium was looked for because we thought it was hot fusion. And of course, tritium is one of the components of hot fusion. Helium was not even considered as a possibility until the hot fusion reaction was removed. So tritium would be the natural, easy one, easy product to look for. So we set up to look for tritium. And we had a whole bench top filled with cells running. And these were essentially sealed, closed cells. And that is, all the gas was captured. It was converted to water by a catalyst, and then it was captured in IV bags. We were the largest user of IV bags in Los Alamos for a while. So that's a distinction that very few people pay any attention to, but I thought I'd mention it because it's a little cool. Anyway, here's a cell, a companion cell running simultaneously. This shows you the scatter. This is the excess. This means 4 times more tritium than initially. This is twice as much tritium as was in the initial cell. This is 4 times. So you can see the amount of scatter. This is well inside the scatter. So we go up. It stays it takes a little while to get started. And then it goes up and stays sort of constant here, and then start up again. Then we get these bursts, and then a slow decay as the tritium is used up. Here's the example of the cell to which I added tritium, and you see it's going along constant, and then I added the tritium, and now it's going along constant again.
What's that response time? What is that step function? Is that a day?
Well, no, that's instantaneous. I mean, you add the tritium and you make the measurements. Tritium's there. Well, we took a measurement, added the tritium, and then took another measurement. And so this point and this point are essentially contemporary. When you make tritium by the cold fusion reaction, it's a slow process. It goes up at some slow rate, and there's also a delay. So there's a very definite difference in the way it behaves between nature doing it and me doing it. Okay. This is Tom will talk about this in more detail, but at Los Alamos there were a large number of people trying to replicate the effect, and only 3 of us succeeded, and that's why we're still in the field. The rest of the people are going about their daily business, and I don't know if that's an advantage or not. But Tom was one of those that had success, and his method was gas discharge, and he'll show you that in great and glorious detail. But this is an example. And here the tritium concentration is measured in the gas by an electrical measurement, a femtotech device that measures the amount of radiation that then generates a small current, which then is measured and related to the amount of tritium. And that's calibrated by then turning the tritium into water, put it in an assimilation detector, and then seeing whether or not you get the same number. Work in Russia was ongoing. It didn't start quite as soon as what we were doing, but it later gained speed. And they were able to make large amounts of tritium by the gas discharge technique. And they, in addition, showed that it's sensitive to the protium to deuterium ratio in the gas in that case. And so those who were unlucky enough to have contaminated their deuterium had success for that reason. And they measured the neutron to tritium ratio, as a number of people have done. I mean, that's a well-known number now. It has a range. The range is partly error, uncertainty, because we're talking about a very low neutron flux, but it's also very possibly related to what's happening in the cell itself. Because when the tritium fuses with a deuteron, it's going to make a neutron. And so it could very well be that secondary reaction is producing a few neutrons that wouldn't be there at all had it not been for that reaction. In Utah, a large amount of money was gotten from the legislature to fund the National Cold Fusion Institute that existed, that was created in Salt Lake City to try to explore this phenomena. They were very successful. They made tritium. Their tritium was even less easily challenged because they used closed cells. They analyzed 90 batches of palladium from all over the world to determine whether or not there was any contamination, and there was not, of course. They were able to analyze the cathode itself. I mean, most people just got the tritium out of the solution or out of the gas. Some of it would remain behind in the cathode, and they analyzed the cathode. And this is the analysis. And you can see the cathode is not uniform. There's a variation. Some places obviously are more nuclear active than others, as you would expect. I mean, this is a very difficult phenomenon to create, and so it's not going to be created very easily or uniformly. So the cathodes have a very heterogeneous behavior with respect to the production of tritium. And you might expect also with the production of helium. Now here's an example of tritium production that was correlated with neutron emission and energetic radiation, which would identify it as hot fusion. And at the time, that distinction was not made, and so this was used as an example of cold fusion with very bursts of neutrons and also gamma rays. And that confused the understanding at the time. Now it's very clear. Hot fusion makes neutrons and radiation, cold fusion does not. And you can tell the difference simply on that basis. So here they had a sample, they're looking at the radiation, and as a function of time, and you see there's nothing. But a sample that was making energy in an electrolytic cell, when there was radiation, the tritium suddenly went up. There was the radiation again, it went up again. And it only produced tritium when the radiation occurred. Now, they were using titanium. Titanium early on was known to produce bursts of neutrons if it were abused. And, you know, most of us do that, but tritium has actually been seen to do that. But anyway, the tritium, by a number of laboratories, including in Italy and in Los Alamos, would subject tritium, expose it to deuterium gas, and then change the temperature. And at certain temperatures, it would give off bursts of neutrons. And that process is called fractal fusion. It's well known now that when a material breaks, forms a crack, that crack has a voltage across between the two surfaces momentarily that is capable, big enough to ionize any deuterium that's present. That's accelerated, and then it smacks into another deuterium and causes ordinary hot fusion. And of course, that happens at a very low rate. I mean, we're not talking about heat production this way. This is just simply an interesting phenomenon of nature. If I take a piece of lithium deuteride, which looks like salt, and put it on the table and hit it with a hammer, I'll get a burst of neutrons. Not a very big burst, but nevertheless a burst, because the fracture causes fractal fusion. Okay. A conclusion. Just to repeat so that those of you who haven't been listening very closely. Tritium production is real. And, you know, if you say that it's not, then I have to accuse you of claiming the world is flat. So, palladium produces tritium without neutrons. Titanium produces tritium with neutrons. It's hot fusion. Tritium production seems to be related to the product of the deuterium and hydrogen concentration in the environment. Tritium production increases with an increase in deuterium in, so the more reactant that's available, the more tritium you get. That's also applies to heat production and presumably to helium production. And tritium and helium production require similar conditions, and therefore it's very logical to assume that they're being generated by the same basic nuclear process. Okay, thank you.
Thank you very much, Ed. Yeah, we can take a few questions now, I think, and I'm going to open the floor up for questions general at the end of the talk, but if you have something specific for Ed, please ask now.
Hi. Do you think that tritium could be a way to have cold fusion and hot fusion, especially DT hot fusion ITER, work together? If you make the mass, the budget of ITER in the last 8 years increased by 10 billion euros. This makes more than 150 dollar increase per month. I mean, with that budget, in 1 month's increase of ITER budget, do you think it would be possible to have a solution to produce tritium, which is not clear yet for ITER project? They're still fighting for find the right material for the blanket and do the tritium breeding.
Well, cold fusion is not going to be a source of tritium. You'll have to get that from a nuclear reactor. And that's a big problem with ITER, because it uses tritium as a raw material, and you have to get that tritium someplace. And as you point out, you have to breed it in the blanket, but that process is too inefficient, and so you have to make that deficit up by some external source of tritium. That external source has to come now from a nuclear fission reactor, which now adds to the expense and difficulty and creates all of its own problems. So you're not going to get out of that problem with cold fusion. We're not going to help you with that. What we will help you with is eliminate ITER completely.
I agree.
Okay.
But they have the budget.
You mentioned that in order to make the economics of ITER and the hot fusion world work, you have to have the tritium. The breeder part of it, therefore, Ed, is essential. I'm over here on the floor. Oh, okay. I asked one of the designers if, in fact, you didn't have to have the breeder part of the reactor, whether or not the problems, essentially, the tokamaks would go away. And he said the problem, if you didn't have to have a breeder, the problem would be very, very much simpler. So I just following up on what was just asked, have you any opinions on the possibilities of large-scale production of tritium using this?
Well, I'm not quite sure what the focus of that question is. The ITER uses a tritium deuterium fusion because it has a lower cross-section. It's easier to produce. You get a higher reaction rate than pure DD. If you could just use DD fusion, then you wouldn't have to worry about tritium. You just generate tritium and sell it to somebody and be happy about it. But so long as you use the tritium as a reactant to make the heat, then somehow or another you've got to replace it. And that's where the problem comes.
Thanks. We'll close down questions. Reserve it for the end and pass the microphone to. I don't.